Hi there, if you can hear me, write a message in the chat so I can just check. Thanks, Henry. Okay, it's 3 o'clock, so I'm going to start. So we have a few people listening in today, and I think a few more who couldn't make the Monday, but who want the recording. So good afternoon, everyone. So this is going to be a bit of an experiment. It's been a while since I've done an online stream, but I did it a few years back for during the COVID, and it seems to work very well. Okay, so I'm going to start off with an introduction of who I am, and then we're going to get started right away. So this is Exponential Asymptotics for the physical sciences. This, in 2024, is one of the taught center courses that's shared amongst a few of the universities in the UK. Okay, so I want to first tell you a little bit about how I'm connected with this subject of exponential asymptotics, and why this is an interesting subject to study, and then we're going to give you some motivating examples, and then we're going to get into some of the history behind divergence theories and asymptotics. Okay, so as I said, my name is Phil Trinh, and I'm a researcher, I'm a reader at the University of Bath. My area is in fluid dynamics, and also in asymptotic analysis. So I use techniques in asymptotics to study very interesting problems, usually in continuum or in fluid mechanics, but more generally in applied mathematics. And I came into this area of exponential asymptotics now a number of years ago, in 2007, 2010, when I did this topic for my PhD. It's a beautiful area of mathematics and of analysis and of applications, and it's something where we have the luxury of many problems, many fascinating problems that we're still continuing to study through the years. Okay, so let's start off with a simple motivating example, because this is the simplest way I can kind of introduce a topic and the scope that we're interested in. Okay. Ooh, this is out of order. Okay. Okay, so I want to start off with this historical example of a crystal growth problem. This was studied in the 1980s, and it's an example that we're going to return to in several chapters or in several lectures time, and we're going to resolve it a bit more completely. So at the moment, this is just to give you an intuition of the kind of asymptotics that you're interested in. So in the 80s, Brewer and Kessler and these other researchers had proposed a geometric model for a crystal growth. So this is, imagine the tip of a snowflake, and the assumption that you're going to use to drive the dynamics of the snowflake tip. So let me just draw this on the board here. So you imagine zooming in near the tip of a snowflake, and you will assume that every point along the snowflake, the motion of that snowflake, of that crystal, is going to be driven as a function of the curvature. So the more highly curved it is, the more it tends to propagate. Okay? And so you introduce an angle, phi, with respect to, I think, the x-axis, you introduce an angle phi for the normal with respect to the x-axis, and you require that this angle should tend to plus or minus pi by 2 at positive and negative infinity along some measure of the arc length, or in this case, the arc length itself. Okay, so I'm going to measure the arc length. Let me call this S. And as S goes to minus infinity, the crystal tip tends to minus pi by 2 in the angle, and it tends to pi by 2 as S goes to positive infinity. Okay? And as I explained, the assumption that we're going to make is that the velocity, Vn, scales with the curvature of the interface, which we call this kappa. And then you need an extra term here, which is a regularizing term. It keeps the system from blowing up. But we're not going to discuss, why you would need this extra term, other than it regularizes the system and keeps it so the interface is regular. Okay, so under those assumptions, you can then write down a differential equation for the angle. And it's written there, and I'll just repeat the equation on the board. It's epsilon squared phi triple prime plus phi prime is equal to cosine of phi. Okay, so this is as a function of S. I need phi to tend to pi by 2 as S goes to infinity, and I need phi to tend to minus pi by 2 as S goes to minus infinity. Okay? So here, you're going to make the assumption that epsilon is a small number, and then in asymptotics, we'll typically write that as epsilon much less than 1. And epsilon positive. Usually I mean epsilon positive, though not always. And I can forget to say that sometimes. Okay. So what some of you might know you should do when you do asymptotic approximations is that you just assume that epsilon is a small number, and therefore at leading order we have to solve this nonlinear differential equation for phi as a function of S. Okay, so we're going to let phi be an expansion in powers of the epsilon, and it makes sense for us because the first term, the error term here, goes up in epsilon squared. It makes sense for us to also proceed in powers of epsilon squared. So phi naught of S plus epsilon squared phi 1 of S plus dot dot dot. Okay? So let's write down some of the equations that we need to solve, and then we're going to see why this is an interesting problem. Okay, so at leading order, so if I just select those terms which don't have an epsilon in them, then I have d phi ds, d phi naught ds is equal to cosine of phi naught. And then I'm going to require phi naught to tend to plus or minus pi by 2 as S tends to plus or minus infinity. And then I can write down a similar equation, which I won't do for phi 1. Actually, it is quite useful to have that equation for phi 1. So let's write it out. So then if I write down those terms which are proportional to epsilon, I'll have phi 1 prime, so d phi 1 ds. And then I have to expand the cosine factor. And so that gives me d phi 1 ds plus phi 1 times sine of phi naught is equal to minus phi naught triple prime. And because the boundary conditions are such that phi tends to plus or minus pi by 2, then in this case, for the correction term for phi 1, you just need that to tend to 0 as you go to infinity. So phi 1 will tend to 0 as s goes to plus or minus infinity. And you can see how you derive all the higher order corrections as you go. Okay, now this equation here is actually a bit of a pain to solve, but you can try to do so yourself. You'd have to integrate d phi naught over phi naught. And you have to go and look up how you do trigonometric substitution, and it is a bit of a pain to do, but you can actually derive the solution in closed form. And if we do so, we'll find out that phi naught of s is minus pi by 2 plus 2 times arctan, or tan inverse of e to the s. Okay. Now, in deriving this equation, notice that we integrated a first order differential equation to get here, right? And so we only had to impose one boundary condition, and the boundary condition that we imposed was that it tends to minus pi by 2 as s goes to minus infinity. But you notice that, in fact, if I put in s to infinity, you get arctan of infinity, and that's essentially pi, and then you can verify that you get pi by 2 in the other limit as well. Okay? So this looks good. It satisfies the boundary conditions, and it's basically a function that goes from minus pi by 2. Let me just draw it here. It goes from minus pi by 2 to pi. And this is, remember, this is in the angle. To pi by 2, sorry, from minus pi by 2 to pi by 2. And remember, this is in the angle, and then when you convert it back and you write x and y in terms of theta or phi, and you integrate up, you can verify this produces the picture that we had before, which is this needle nose crystal. So it seems to be quite good. You know, we came to this model, this geometric model of crystal growth. We derived an asymptotic solution. It looks exactly like what you'd think it should. And if you wanted to, you can go to one order higher and develop the phi 1, and I'll write that out in a minute. But there's an issue. So in fact, let me write down the order epsilon equation for phi 1 now. Okay, so now I take this solution here for phi naught. I have to differentiate it 3 times. I have to put it into the sine of phi naught, and then I have to integrate this function. But you can do so, and you get, so at order epsilon, if you continue and you get phi 1, you'll have minus 2 plus s minus 2 times tanh of s plus a constant times sech of s. Okay. So if you don't remember your hyperbolic functions, the point is that this sech of s function satisfies the necessary boundary conditions as you go to minus infinity and as you go to positive infinity, and indeed this function is 0 at minus infinity and positive infinity, and so the angle still tends to minus pi by 2 and pi by 2. You'll also notice a bit of a suspicious point, which is that this constant here is undetermined. So any value of that constant is permissible, and your equation, your asymptotic solution still satisfies the necessary boundary conditions. Okay. If you were to continue this procedure, it gets harder and harder, obviously, because the higher you go, the more convoluted the algebra becomes. But you can verify that at every asymptotic order, phi naught, phi 1, phi 2, etc., it always satisfies the necessary boundary conditions. And so it seems the asymptotic solution that you develop seems to satisfy the problem to all orders, to all algebraic orders. Okay, so this is very weird, it turns out, because the problem that we've written down, the original differential equation, in fact, has no solution. Okay, and so let's have a look at how you might come to that conclusion if you were to look at the numerical results. Okay, so here you'll see that I've written just a little Python code. I'll upload this Python code somewhere where if you want to play with the code, you can do so. But essentially this code is just solving that third order problem. Okay, it converts that third order problem to a system of first order differential equations, and then it sets for this code, you can see the epsilon parameter is set to be 0.01. Now the next few lines after the parameters that you see, you'll see it sets the initial conditions, and not knowing any better, because we're not quite sure what we should be setting for the initial conditions, we're just going to make it so that at minus infinity, we're going to start at roughly near pi by 2. So minus pi by 2 plus some small epsilon, 10 to the minus 4. And then I'll set my higher derivatives to 0 because I think it's going to be flat upstream. You can see the next few parameters. I'm going to solve it along the domain from s is equal to minus 10 to s is equal to 20. I'm going to solve it with 500 steps to evaluate the solution. And then this is shoved into a Runge cut of 45 ODE solver, and then you can kind of see we're going to extract the solution and we're going to plot the solution. Okay, so the next few pictures are plots of the solution at different values of epsilon. So here, this first one is with epsilon is equal to 0.1. You can see the numerical solution is in blue, and the asymptotic solution is, the leading order asymptotic solution is dashed and in red. Okay, and so this looks a bit suspicious, right? The growing modes, the growing oscillations as you go to positive infinity definitely seems to invalidate the necessary boundary conditions. So you might, if you're doing this numerically, you might have some thoughts. Well, okay, maybe this is numerical error. Maybe my epsilon is too big. Maybe I should be taking epsilon to be smaller. Maybe I didn't start far enough to the left. Maybe I started off with the wrong boundary condition. So you might twiddle each of the parameters in that discussion and then see whether you have the same kind of picture. So now this is with epsilon equal to 0.01, okay? And you see it seems to match the underlying phi naught solution really well, but then as you go to infinity in S, something seems to be happening and you have a growing mode again, which is contaminating the numerical solutions. And again, this doesn't look like it should be a numerical solution. And as well, you can decrease epsilon now to 0.001, and you see there's still the same issue. It matches the leading order very well, but then some kind of oscillation, some kind of wiggle kicks in. Now, if you were an experimentalist and you were studying this kind of problem, what would you try to do? Well, again, you might think this is numerical error. You might think that I just haven't got one of the parameters right. I'm going to keep on trying. One of the things that you might do is if I go back to one of these oscillation pictures, you might try to measure the amplitude of these oscillations. Okay, so you might, for example, you might look at the third maxima or minima and then calculate the amplitude at this value of epsilon, and then decrease your value of epsilon, and then calculate the amplitude and decrease it and calculate the amplitude, and so forth and so on. So that's, if you're an experimentalist, that's something that you might do. And what would you find if you did that? That little experiment. You would find that if you were to plot a graph of 1 over epsilon, and you were to plot a graph of the amplitude, or the logarithm of the amplitude of these oscillations, you would see, in fact, that it looks like a straight line. It tends to a straight line. And as epsilon goes to 0, you're going to infinity to the right here. And because this is a straight line, if the logarithm of the amplitude is a straight line, then that tells you that the amplitude is scaling as e to the minus some constant over epsilon. You can see that, of course, if I take the log of that, I have minus k over epsilon plus constant. Okay? And so you would be able to experimentally verify, or numerically verify, that whatever the reason for whatever's going on, these ripples which are contaminating your solution turn out to be exponentially small. So with that in mind, what does that suggest actually for your asymptotic approximation? Well, it suggests that now you know that your phi, or at least you have the suspicion that your asymptotic solution that you derived before works, right? It matches the numerics. And as epsilon gets smaller and smaller, the fit seems to get better and better. And if you were to add the next term, again, the fit gets better and better. But it seems that what you're missing is, in fact, a term which is exponentially small. And it's multiplied by an oscillation. And again, if you were to do this numerical experiment, okay, if you were to do this numerical experiment and measure not only the amplitude, but if you were to measure the wavelength between the peaks of your solution, you would find out that they also scale as a function over epsilon, so that the wavelength is 2 pi times epsilon, and that the wavelength is getting smaller and smaller as epsilon goes to 0, plus a phase shift. Okay? So in fact, it's not that simple. There might be an algebraic power here that you don't see because you're not going to see it to this accuracy in your experiments. So this term is exponentially small. This term is smaller than every term in the regular perturbative expansion. And so you would say that this term is beyond all orders. Beyond all orders of the regular expansion. And this is the exponential asymptotics. Okay? So this, the answer, by the way, to the question of the original differential equation is that there is no solution. This third order problem, for which you require the solution to tend to minus pi by 2 to pi by 2, for reasons that we've not quite articulated, there is no solution that satisfies those boundary conditions. And yet, that's very puzzling, right? Because not only did we derive a solution to all algebraic orders that satisfies the necessary boundary conditions, but actually that solution that we derive looks quite good. And this is shown here in the slide in the top right there. That's the solution, the leading order solution that we derive. It matches our physical intuition of the problem. But the basic answer is that your model is wrong and you're missing potentially some terms. Either you need to go back and rethink the boundary conditions in this model, or you need to add some additional terms that somehow will deal with this effect. But it's very peculiar, right? If you do asymptotic approximations, or if you do asymptotics, usually you never encounter a situation where it turns out that you were developing an approximation that satisfies all the necessary terms to all orders, and yet it turns out that there is no solution. And that is one of the dangers of working with formal methods. So a lot of analysts will say, well, a lot of asymptotics is formal. You're positing a solution. You're positing expansion for a solution that may not exist, or may not exist in the form that you think. Okay. So what are some takeaways from this motivating example? I'd like to come back and derive these exponential asymptotics for you, but we're not going to do that, at least for a few lectures, because we're going to need some techniques to allow us to derive these terms. But what are some takeaways from this? Well, the first important takeaway is about the peculiar behavior of that asymptotic expansion. Okay? And so this is one of the key items to keep in mind. I'm going to tell you 3 items, 3 lessons that we have from studying this crystal growth problem. And the first one is about asymptotic divergence. Okay, so this is important enough for me to go into detail here. So I want to write down the phi naught problem that we had before. Okay, so let's write down phi again. So this is phi naught plus epsilon squared phi 1 plus epsilon to the 4 phi 2 plus so forth. And we found that phi naught was minus pi by 2 plus 2 times arctan of e to the s. Okay? But remember here, well, I say remember, you're going to have to look it up, but there's a relationship between arctan and logs. So you have to recall here that arctan of u is I over 2, the log of u minus I over u plus I over u minus I. Okay? Okay, so this arctan function is potentially singular where the arguments are plus or minus I. So this function has singularities where e to the s is equal to plus or minus I. And so it has singularities when s is plus or minus pi I over 2 plus all the 2 pi I multiples plus 2 pi I z up the imaginary axis. So this is a function, if you were to look at this function in the complex plane, let me draw that here, and if I were to plot the real part of s and I plot the imaginary part of s, you would notice a series of singularities that start at pi I over 2 up the axis, and they go up and down. So the significance of this is not obvious at the moment, right? Okay, but let's keep that in mind, that this function is singular at those points. Now, and in fact, so you conclude that phi naught has a log singularity at s equal to plus or minus pi I over 2, etc. And the key question to ask is what happens when you go to higher order in your asymptotic approximations. Okay? So to get phi 1, note that to get phi 1, you had to, to get phi 1, the equation you had was phi 1 prime plus phi 1 times sine of phi naught is equal to minus phi naught triple prime. And so in order to get the equation in order to get phi 1, you have to basically differentiate phi naught 3 times and then in essence integrate it once. So you kind of have to differentiate phi naught twice if you count it in a rough way. Okay? And what happens is that if you have that logarithmic singularity at leading order, then the power of that singularity increases. So you can verify that phi 1 has a singularity of order 2. So i.e. phi 1, as you approach that singularity, will behave like a constant times s plus or minus pi I over 2 to the minus 2. And then again, when you go to the next order in phi 2, you're going to have the same issue, which is that the embedded singularities in phi 1 or phi naught will amplify the higher up you go. And so every order that you proceed, not only does the singular behavior get worse, you have a 1 over factor to a higher power, but in fact every time you differentiate, this number needs to come down, and so it becomes 2 times 4 times 6, etc., and you're going to have a factorial growth on the top. So that tells you that if I were to, in my thought experiment, so imagine in my numerical, when I actually want to compute anything with asymptotics, I like to set a value of epsilon, so I'm going to take epsilon to be a number, and then suppose I'm going to fix the value of s on the real axis, because I'm only interested in real numbers. And I compute phi naught, and I compute phi 1 and phi 2 and phi 3 and so forth. Okay? Then no matter where I am in the complex plane, eventually this divergence is going to kill me, right? And the point is that epsilon to the n times phi n will tend to infinity as n goes to infinity. Okay, so that's important enough for me to just state here in words. So because there exist singularities in phi naught, phi 1, etc., for any epsilon small, for any fixed epsilon small, right, we're always fixing epsilon to be 0.01 or 0.001 in our numerics, and any fixed s, it will be that epsilon to the n times phi n will tend to infinity as n tends to infinity. Okay, for non-pathological problems, right? You can probably make some pathological problem where the value of s you take is such that this doesn't happen, but in general, this must happen. And so you would come to the conclusion that your series expansion diverges. Okay. And this logic that we've applied seems to work regardless of the differential equation you have. Because any singular differential equation will typically involve epsilon times the highest derivative. In this case, there's an epsilon squared times phi triple prime plus dot to dot. And the point is that when you apply the asymptotic procedure, to get the next term of the sequence, you always have to differentiate the previous terms. And so as long as your earlier terms have a singularity somewhere in the complex plane, you have the potential to amplify it to the extent where the whole series diverges. And this is not a pathological thing. This is actually routine for almost all singular perturbative problems that you're going to meet. So this brings up a very interesting philosophical and mathematical question, which is, what does it mean to approximate something well-behaved, a solution of a problem? This solution might represent some physical phenomena. What does it mean to approximate it with a divergent series? And this is the crux of the issue. It's our understanding of this weird manipulation. To what extent should we just use phi naught to approximate the function? And when isn't that going to get us into trouble? Some of you might use asymptotics in your own research or your own studies, and you would have never encountered this issue because usually it's a pain in the bum to go that high. You always just get one or two terms from the asymptotic approximation. You never go to infinity, and so you never have to think about what happens as n goes to infinity. Okay? So that was one key takeaway from this crystal growth problem, which is the asymptotic approximation for our crystal growth problem diverges, and part of exponential asymptotics, part of our understanding of asymptotics is going to depend on our understanding of that phenomena, this divergence. Okay. Now, what's the second point to make? Always seems to restart. The second point to make is that the exponential correction that I've just given you is just the tip of the iceberg. In fact, it gets a lot worse, right? So what do I mean? Well, I mean that the correction that I wrote down is a over epsilon to the gamma and then something exponentially small. But in fact, this here is just the first term that we have to figure out, or we'd like potentially to figure out. If I move the a and I take this a 1 over, in fact, that was the a naught of s, which became a cosine. We actually have an epsilon squared correction of that. And then an epsilon to the 4 correction of that. And then, if you're feeling particularly masochistic, you might ask, does that series diverge? And the answer is, it probably does. In fact, it gets even worse than that, because this is a nonlinear problem. The differential equation was nonlinear. You remember, it had a sine or a cosine of phi. And so that means that if it has a sine of phi and a cosine of phi, and if you begin to expand things, then you're going to have powers of phi. Which means that if you have a contribution like e to the minus k over epsilon, and you start taking powers of that, then you must also have contributions like e to the minus 2k over epsilon times an asymptotic approximation. And if you have e to the minus 2k over epsilon, you should have e to the minus 3k over epsilon, and so forth and so on. So if you're taking courses on asymptotic approximations, you would have only dealt with this one here. Phi naught, if you're lucky, you'll get phi 1 and phi 2 and so forth, and it gets harder and harder as you go. Here I'm pointing out that actually there are exponentially small terms with respect to the base expansion, but also multiples of the epsilons, and it gets worse and worse and more complicated. Okay, so this is actually present in this problem, but you can ask yourself as well, do I really need to know this? Is this ever going to be important? And that's one of the interesting questions to think about. Okay. Now, the third point I said I was going to give 3 important facts that we've learned from doing this crystal growth problem. The first one was about the fact that the asymptotic approximation diverges. The second is that there exists this beyond all order structure, of which I've started to illustrate for you here, this tower of divergent asymptotic approximations. And this, again, is not a pathology in this problem. This happens in all interesting nonlinear problems. And the fourth, and maybe the most important question here is if it's exponentially small. So we've been trained to think that if something is exponentially small, then it's negligible, it's not too important, you don't have to think about it. And this is an example, this crystal growth problem is an example that that is not true. Remember that when you talk about exponential smallness, you always have to talk about a limit, right? It's exponentially small as it goes to infinity or minus infinity. It's exponentially small if epsilon goes to 0. So you always talk about exponential smallness in a limit. But in practice, when you solve any real problem, you're setting a value of epsilon, right? You put in epsilon as 2, you put in epsilon as 1, you put epsilon 0.1, 0.01. So just in terms of practical asymptotics, this is a really important distinction that a lot of even very experienced people don't understand, which is that exponential smallness is in the theory where epsilon tends to 0, but in practice you always set a value of epsilon. And so your physical phenomena that you're looking to model might say, well, epsilon is 0.1, and in that case, the size of your contributions is finite. It's a number, right? And that number may be physically important, right? So remember that there are a variety of problems, and we're going to see this during the next few lectures. There are problems where the exponential asymptotics is observable. They capture some important physical effect like water waves or some other thing. And in those situations, it turns out that physical effect is important for you to capture. So it is not negligible. Okay? The second kind of problem that we encountered from this crystal growth is a problem of existence and non-existence. And in this case, we see that the epsilon, the exponential asymptotics being in there is actually important enough because it allows you to validate or invalidate a necessary boundary condition. So it separates your problem from having solutions or not having solutions. And this is another kind of important subclass of problems in exponential asymptotics where it's important to characterize those exponential asymptotics because they can mean the difference between having a solution or not having a solution, or providing some kind of intrinsic selection mechanism in your problem. And we will have examples of that as well through this course. Okay. I want to kind of end with some historical notes, and then we're going to continue those historical notes in the next lecture. And I'm not an expert on the history of divergent series, of asymptotic approximations. And by now, hopefully you understand there's a connection between asymptotic approximations and divergent series. The two subjects are intrinsically linked. But I want to give you an overview of what I understand, and perhaps as this course develops, we're going to flesh more of this out. Okay, so I would divide the history of asymptotics into kind of three categories. And part of the problem with trying to really go into detail about the history of divergent series is because different researchers had focused along different directions. So one category of research is what I would call practical asymptotics. And going as far back as the 1600s, there are many mathematicians and physical scientists which had used divergent series with no ill effect, because they understood that that these series gave excellent approximations, even though the reasons why they worked was not necessarily well understood. Secondly, there's a branch of mathematics where the mathematicians were interested in trying to nail down the exact theory of asymptotic approximations and divergent series, to characterize what it means for a series to be asymptotic. And now, when we did the demonstration on the board, we didn't think about it. We just wrote down a series in powers of epsilon, grouped everything in powers of epsilon, and solved order by order. And then finally, there is a branch, an important branch of asymptotic approximations, where the question was, given a divergent series, how do you ascribe meaning to that divergent series? And that leads to questions of summability. Okay? So, how does it start? Well, it goes back, I think, as far back as the 17th century. Leibniz and Bernoulli, James Bernoulli, which I think is the father of all the Bernoullis, were already thinking about questions of how do you interpret the sum of 1 minus 1 plus 1 minus 1 plus 1, etc. Though at the time, I think this question was more out of interest. It was philosophical rather than practical. But there were practical reasons to answer this question, which would be dealt with in a few decades. Okay? The earliest kind of work with divergent series is generally attributed, beyond this question of 1 plus 1 minus 1, etc., is generally attributed to James Stirling. And this is a picture of, I think, a plaque that appears in Scotland, where James Stirling was from. And Stirling had written a book, or a series of books, at one point in his life, about the expansion of what's known as Stirling's of the factorial function, what's known as Stirling's formula, and you see these formulae in there. So he was already manipulating divergent series. This series is divergent, and he had used it to calculate something like the logarithm of 1,000 factorial, already in the 18th century. A little bit later, Euler throughout his works had examined a variety of questions related to divergent series, and he had written about this exact 1 minus 1 plus 1 series, and he argued that it was essentially a half, and he gave a few different reasons for this. By the way, Leibniz, earlier I said, had talked about this series. Leibniz's argument was it's 1 or minus 1 if it's even or odd, and so it hits 1 or minus 1 with equal probability, and so you should average it out to be a half. That was Leibniz's argument. But Euler presented a different argument for why one should ascribe the sum, the value of a half to this series that doesn't converge. So this was 17th century and early 18th century. And then what happened was the French got into it. And so this is quite well known. At around the mid 1800s, Niels Abel and Cauchy had led a very important group of analysts in France. And the intention of this group of analysts was essentially to make all of mathematics rigorous, right? And that's why France went down this route in the 1800s of everything needs to be rigorous. And in this work by Abel, so this was in 1826, you see this quotation of divergent series are in general the work of the devil. This was written in French. Divergent series are in general the work of the devil, and it's shameful to base on any demonstration whatsoever, whatever on them. The most essential part of mathematics is without basis. For the most part, the results are valid, if it is true, but it is a curious thing. I'm looking for the reason, and it is a very important problem. And then a later quotation here by this work in 1969. What affected the history of divergent series most were the pronouncements of Cauchy and Abel, so that a hiatus of approximately 45 years developed in which very few dared to publish conclusions about their series and contradict these two eminent mathematicians. So in fact, there was very little interesting research that proceeded from the perspective of mathematicians, though I'll say a few words of again, pure mathematicians about divergent series, because the word was out that you shouldn't be using them. Now, at the same time, in the 1800s and even in the 1700s, there were plenty of people who were using them to great success. Okay, so Laplace, Pierre-Simon Laplace was the Frenchman who developed many still powerful techniques that we use every day in asymptotic approximations. George Green, Liouville, Stokes, and Kelvin. And many of these, Laplace and Liouville were French mathematicians. The others were British applied mathematicians. So certainly there were, in Britain, there was a big tradition of using asymptotics, and it was very important in the field of celestial mechanics, which was a very important problem in that era. Okay. Now, essentially, moving to the end of the 1800s, there were two important works, of which one was by Stilties and the other by Henri Poincaré. And essentially, the value of these works, so Poincaré had written a series of 3 manuscripts. For celestial mechanics, this was essentially to attack the n-body problem, though he applied it to the 3-body problem and the restricted 3-body problem. And Poincaré acknowledged in his works that mathematicians and astronomers mean different things when they work with what we understand as divergent series, right? A mathematician would look at a divergent series and say, well, the series diverges to infinity, and so it's no good. Whereas an astronomer would look at that series and say, well, it produces an excellent approximation. In fact, it produces an approximation, a better and better approximation as I take more and more terms up to some point, and then it diverges. And Poincaré was very respectful. In fact, if you read his works, he was very respectful of both of these viewpoints. Okay? And in his manuscripts, Poincaré essentially tries to get to the essence of what it means to, for a series to be asymptotic. He gave a definition of what an asymptotic approximation is, and that's something that we're going to revisit. Stilties, on the other hand, had written his thesis in 1886 on problems largely in number theory and in pure mathematics. I include that little quotation here that in June of 1886, Stilties' doctoral thesis was published in the Annals, and the title of the thesis was Recherche sur quelques séries semi-convergentes, so research on several semi-convergent series, and it was only 58 pages long, didn't have any footnotes, and it didn't have any bibliography, but it was enough to pass at that time. And he looked at some of the problems that you see listed here, like studying this logarithmic integral and studying other integral approximations, and then also studying a differential equation. Trying to get to the heart of this issue of divergence. And so we're going to end the current lecture here, but in the next lecture, what I'm going to do is I'm going to look at what Stieltjes had done to study that logarithmic integral. We're going to try to essentially write down a series approximation, an asymptotic approximation with a remainder term, and then attempt to study that remainder term in order to gain an understanding of the consequence of asymptotic divergence. Okay, so that's the end of this lecture. I'm going to end the recording now, and if any of you have any questions, then you can feel free to send me an email or write a message in the chat. But otherwise, I will see some of you on Wednesday at 3 p.m. Thanks.